Welcome to today's Explainer. We're diving straight into a literal turning point in scientific history, the Stern-Gerlach experiment. This elegantly simple test fundamentally shifted our understanding of how the universe operates at the microscopic level, cracking open a quantum mystery that pretty much birthed modern technology. So let's break down exactly how they did it, step by step. Classical versus quantum? Who was right? To really grasp the stakes of this experiment, we got to step back to the 1920s. The physics community was facing an absolute high-stakes showdown. Classical physics was the undisputed champion, right? It had perfectly described macroscopic phenomena for centuries. But this new, emerging quantum theory was making some frankly bizarre predictions about the atomic world, specifically regarding spatial quantization, that completely contradicted classical thought. The scientific community needed proof. They needed a definitive test to see which framework actually governed reality. Okay, let's dive into this and look at exactly what these two sides were arguing about. Classical physics predicted that tiny atomic magnets should behave like regular compass needles, meaning they could point in any continuous direction. If you pass a beam of these atoms through a magnetic field, they should just spread out evenly into a smooth smear. Quantum theory, however, argued, no way. These atomic magnets cannot just point anywhere. Instead, only discrete, locked orientations are allowed. It's kind of like the difference between sliding down a smooth ramp versus standing on specific steps of a staircase. They were two completely, totally incompatible visions of reality. So enter the investigators who actually set out to test these bounds of reality, Otto Stern and Walther Gerlach. They designed a physical apparatus to capture the invisible behavior of the atomic world. And you have to imagine, the tension in their Frankfurt laboratory must have been absolutely palpable. They knew that whatever result their machine produced would either validate the centuries-old classical view or confirm this strange, stair-step reality of quantum mechanics. Their remarkably clever setup worked like this. Step 1, they heat silver atoms in a furnace to produce a precise, narrow, forward-shooting beam. They specifically chose silver because its single unpaired outer electron gives the atom a measurable intrinsic magnetic moment, all without interference from orbital angular momentum. Step 2, they pass this fast-moving beam through a non-uniform magnetic field. Because each silver atom is essentially a tiny magnet, the magnetic field exerts a force on it. And where that force pushes them? Well, that's exactly what solves our mystery. The big reveal, 2 separate spots. Now, what's really interesting about this result is how wildly it defied expectation. Instead of the classical prediction of a continuous smooth spread, the scientists observed 2 distinct spots. The beam split cleanly in 2. This was an absolute earthquake in the physics community. It definitively proved that the magnetic moment can take only specific orientations. Quantum theory was right. Reality at the atomic scale is discrete, not continuous. So the crucial point is understanding the mechanics of how this split actually occurs. The force on a magnetic dipole in a non-uniform magnetic field follows a really elegant physical principle. Force, or F, is proportional to the magnetic moment, mu, multiplied by the magnetic field gradient, dB over dz. Because quantum mechanics dictates that the magnetic moment can only point in locked directions, the resulting force pushing on the atoms comes only in specific, discrete amounts. So why exactly 2 spots, rather than 3 or 4 or 100? It all comes down to the fundamental quantum properties of silver atoms. Silver atoms have a spin quantum number, represented by S, of exactly 1/2. According to quantum mechanics, this allows for only 2 possible spin projections, positive 1/2 and negative 1/2, essentially spin up and spin down. With no in-between allowed, the force we just talked about pushes the atoms in only 2 distinct directions, splitting the beam perfectly in 2. It's amazing how this seemingly magical behavior is grounded in such a simple mathematical rule. Now, you might be thinking, this sounds like fascinating atomic trivia, but it actually changed the world. And this brilliantly illustrates the incredible power of foundational science. The Stern-Gerlach experiment laid the groundwork for an astonishing array of real-world applications. Because we understood quantum spin from this experiment, we eventually developed MRI machines, saving countless lives. It paved the way for modern quantum computing, precision atomic clocks, and nuclear magnetic resonance. All of these towering technological achievements literally trace their roots back to a silver beam in a 1922 furnace, proving that quantum spin is discrete. If one experiment with silver atoms unlocked quantum computing and MRIs, what reality-bending technologies are hiding inside today's unresolved scientific mysteries? It really makes you pause and think about the future. What mind-blowing innovations are waiting for the next great experiment to crack them open? Science is a continuous, thrilling journey, And I hope this explainer has sparked your curiosity to keep exploring the universe around us. Keep questioning, keep learning, and I'll catch you in the next explainer.